1945, government officials in Grand Rapids, Michigan did something no one else has done. They began to fluoride its public water supply, that is, putting fluoride in tap water. 5 years later, school children there were found to have significantly fewer cavities. Other Michigan cities followed with similar results. And since then, cities around the US have used water fluoridation to prevent dental diseases, and other countries have done the same. Decades later, CDC would call that small experiment at Grand Rapids one of public health's greatest success stories. Millions of people have enjoyed fluoride's protection, and the tooth decay rate has plummeted.
However, recent discoveries in certain strains of bacteria raises cause for concern. The protections that fluoride offers us may soon vanish, leaving millions of people's health at stake. To unravel the mystery of how this came to be, we look to decades of bacterial evolution and 2 little-known proteins. For decades, fluoride has been used by humans to fight bacteria, with initial research on its effects dating all the way back to 1901. It has several means to reduce bacterial activities or even eliminate bacteria in their entirety. One of the most important ways fluoride fights bacteria is through its ability to reduce the acid tolerance of bacteria. With even low levels of fluoride, reducing this acid tolerance can cause complete arrest of glycolysis of bacteria such as Streptococcus mutans. You perhaps are most familiar with fluoride for its dental effects. Fluoride works well in protecting our dental health since dental plaques are mostly acidic environments. Thus, bacteria here are greatly affected by a reduction of their acid tolerance.
However, the bacteria are fighting back. Researchers have discovered that some bacteria have developed a mechanism to fend off fluoride. Using that mechanism, bacteria were able to identify fluoride and eject it from its system. This mechanism is an RNA structure called a fluoride riboswitch. Riboswitches are attached to specific genes and bind to small molecules, resulting in a change in the production of the proteins encoded by the mRNA. Thus, genes with riboswitches are able to regulate their own activity depending on the small molecule they choose to bind to, such as fluoride. When the riboswitch activates after binding to fluoride, it can turn on certain gene codings in order to produce genes that help bacteria transport fluoride out of the cell. This mechanism thus helps bacteria mitigate the toxic effects of high levels of fluoride and allows them a better chance of evading fluoride protection. There are important potential consequences to bacteria developing fluoride resistance. The average adult spends $1,000 per year on dental care and cavities, and this number will continuously increase if fluoride can't provide its benefits for oral health. Scientists are attempting to mitigate fluoride resistance by researching its flaws in order to make smaller concentrations of fluoride even more lethal to bacteria. They're also trying to accomplish this goal by targeting the fluoride riboswitch genes when developing drugs in the future to extend the protection provided by fluoride.